Good evening, and thank you for joining me for another Boring Books for Bedtime. I hope tonight's selection provides all the boredom your busy brain needs to quiet down and let you get some sleep. Before we begin, I'd like to give a special shout out of thanks to some new members of our Patreon family. Justin, Jennifer, Lover of Unreasonable, Suzanne, Kate, Michelle, and Tom. Thank you all so much for supporting this podcast. By becoming members of Patreon, you help us remain 100% listener-supported and ad-free for everyone, and it's very much appreciated. If you're interested in supporting Boring Books for Bedtime and finding out more about the perks available to subscribers, including exclusive episodes heard nowhere else, you'll find a link to Patreon in the show description. You'll also find a link to buymeacoffee.com, where you can support us with a one-time tip, no subscription required. I hope you'll take a moment to check them out. Now, let's read and relax. Find a comfortable spot. Adjust your volume. Take a nice deep breath in. Let it out slowly. And off we go. Tonight, let's relax with some more science as we work our way through the ABC of Relativity by Bertrand Russell, author of The Principles of Mathematics, Proposed Roads to Freedom, and Why Men Fight. First published in 1925 by Harper and Brothers, New York and London. Let's pick up right where we left off at the beginning of Chapter 7. Let's begin. Chapter 7: Intervals in Space-Time. The special theory of relativity, which we have been considering hitherto, solved completely a certain definite problem to account for the experimental fact that when two bodies are in uniform relative motion, all the laws of physics, both those of ordinary dynamics and those connected with electricity and magnetism, are exactly the same for the two bodies. Uniform motion here means motion in a straight line with constant velocity. But although one problem was solved by the special theory, another was immediately suggested. What if the motion of the two bodies is not uniform? Suppose, for instance, that one is the earth while the other is a falling stone. The stone has an accelerated motion. It is continually falling faster and faster. Nothing in the special theory enables us to say that the laws of physical phenomena will be the same for an observer on the stone as for one on the earth. This is particularly awkward, as the earth itself is, in an extended sense, a falling body. It has at every moment an acceleration towards the sun, which makes it go round the sun instead of moving in a straight line. As our knowledge of physics is derived from experiments on the earth, we cannot rest satisfied with a theory in which the observer is supposed to have no acceleration. The general theory of relativity removes this restriction and allows the observer to be moving in any way, straight or crooked, uniformly or with an acceleration. In the course of removing the restriction, Einstein was led to his new law of gravitation, which we shall consider presently. The work was extraordinarily difficult and occupied him for 10 years. The special theory dates from 1905, the general theory from 1915. It is obvious from experiences with which we are all familiar that an accelerated motion is much more difficult to deal with than a uniform one. When you are in a train which is traveling steadily, the motion is not noticeable so long as you do not look out of the window. But when the brakes are applied suddenly, you are precipitated forwards, and you become aware that something is happening without having to notice anything outside the train. Similarly, in a lift, everything seems ordinary while it is moving steadily. But at starting and stopping, when its motion is accelerated, you have odd sensations in the pit of the stomach. We call a motion accelerated when it is getting slower as well as when it is getting quicker. When it is getting slower, the acceleration is negative. The same thing applies to dropping a weight in the cabin of a ship. So long as the ship is moving uniformly, the weight will behave, relatively to the cabin, just as if the ship were at rest. If it starts from the middle of the ceiling, it will hit the middle of the floor. But if there is an acceleration, everything is changed. If the boat is increasing its speed very rapidly, the weight will seem to an observer in the cabin to fall in a curve directed towards the stern. If the speed is being rapidly diminished, the curve will be directed towards the bow. All these facts are familiar, and they led Galileo and Newton to regard an accelerated motion as something radically different in its own nature from a uniform motion. But this distinction could only be maintained by regarding motion as absolute, not relative. If all motion is relative, the Earth is accelerated relatively to the lift, just as truly as the lift relatively to the Earth. Yet the people on the ground have no sensations in the pits of their stomachs when the lift starts to go up. This illustrates the difficulty of our problem. In fact, though few physicists in modern times have believed in absolute motion, the technique of mathematical physics still embodied Newton's belief in it, and a revolution in method was required to obtain a technique free from this assumption. This revolution was accomplished in Einstein's general theory of relativity. It is somewhat optional where we begin in explaining the new ideas which Einstein introduced, but perhaps we shall do best by taking the conception of interval. This conception, as it appears in the special theory of relativity, is already a generalization of the traditional notion of distance in space and time, but it is necessary to generalize it still further. However, it is necessary first to explain a certain amount of history, and for this purpose we must go back as far as Pythagoras. Pythagoras, like many of the greatest characters in history, perhaps never existed. He is a semi-mythical character who combined mathematics and priestcraft in uncertain proportions. I shall, however, assume that he existed, and that he discovered the theorem attributed to him. He was roughly a contemporary of Confucius and Buddha. He founded a religious sect which thought it wicked to eat beans, and a school of mathematicians who took a particular interest in right-angled triangles. The theorem of Pythagoras, the 47th proposition of Euclid, states that the sum of the squares on the two shorter sides of a right-angled triangle is equal to the square on the side opposite the right angle. No proposition in the whole of mathematics has had such a distinguished history. We all learned to prove it in youth. It is true that the proof proved nothing, and that the only way to prove it is by experiment. It is also the case that the proposition is not quite true. It is only approximately true. But everything in geometry, and subsequently in physics, has been derived from it by successive generalizations. The latest of these generalizations is the general theory of relativity. The theorem of Pythagoras was itself, in all probability, a generalization of an Egyptian rule of thumb. In Egypt, it had been known for ages that a triangle whose sides are 3, 4, and 5 units of length is a right-angled triangle. The Egyptians used this knowledge practically in measuring their fields. Now, if the sides of a triangle are 3, 4, and 5 inches, the squares on those sides will contain respectively 9, 16, and 25 square inches, and 9 and 16 added together make 25. 3 times 3 is written 3 squared, 4 times 4, 4 squared, 5 times 5, 5 squared, so that we have 3 squared plus 4 squared equals 5 squared. It is supposed that Pythagoras noticed this fact after he had learned from the Egyptians that a triangle whose sides are 3, 4, and 5 has a right angle. He found that this could be generalized, and so arrived at his famous theorem. In a right-angled triangle, the square on the side opposite the right angle is equal to the sum of the squares on the other two sides. Similarly, in 3 dimensions, if you take a right-angled solid block, the square on the diagonal, the dotted line in the figure above, is equal to the sum of the squares on the 3 sides. This is as far as the ancients got in this matter. The next step of importance is due to Descartes, who made the theorem of Pythagoras the basis of his method of analytical geometry. Suppose you wish to map out systematically all the places on a plane. We will suppose it small enough to make it possible to ignore the fact that the earth is round. We will suppose that you live in the middle of the plane. One of the simplest ways of describing the position of a place is to say, starting from my house, go first such and such a distance east, then such and such a distance north, or it may be west in the first case and south in the second. This tells you exactly where the place is. In the rectangular cities of America, it is the natural method to adopt. In New York, you will be told to go so many blocks east or west, and then so many blocks north or south. The distance you have to go east is called X, and the distance you have to go north is called Y. If you have to go west, X is negative. If you have to go south, Y is negative. Let O in the diagram be your starting point, the origin. Let OM be the distance you go east, and MP the distance you go north. How far are you from home in a direct line when you reach P? The theorem of Pythagoras gives the answer. The square on OP is the sum of the squares on OM and MP. If OM is 4 miles and MP is 3 miles, OP is 5 miles. If OM is 12 miles and MP is 5 miles, OP is 13 miles because 12 squared plus 5 squared equals 13 squared. So that if you adopt Descartes' method of mapping, the theorem of Pythagoras is essential in giving you the distance from place to place. In 3 dimensions, the thing is exactly analogous. Suppose that, instead of wanting merely to fix positions on the plane, you want to fix stations for captive balloons above it. You will then have to add a third quantity, the height at which the balloon is to be. If you call the height z, and if r is the direct distance from O to the balloon, you will have r squared equals x squared plus y squared plus z squared. And from this you can calculate r when you know x, y, and z. For example, if you get to the balloon by going 12 miles east, 4 miles north, and then 3 miles up, your distance from the balloon in a straight line is 13 miles, because 12 times 12 equals 144. 4 times 4 equals 16. 3 times 3 equals 9. 144 plus 16 plus 9 equals 169, which equals 13 times 13. But now suppose that instead of taking a small piece of the Earth's surface, which can be regarded as flat, you consider making a map of the world. An accurate map of the world on flat paper is impossible. A globe can be accurate in the sense that everything is produced to scale, but a flat map cannot be. I am not talking of practical difficulties. I am talking of a theoretical impossibility. For example, the northern halves of the meridian of Greenwich and the 90th meridian of west longitude, together with the piece of the equator between them, make a triangle whose sides are all equal and whose angles are all right angles. On a flat surface, a triangle of that sort would be impossible. On the other hand, it is possible to make a square on a flat surface, but on a sphere it is impossible. Suppose you try on the Earth. Walk 100 miles west, then 100 miles north, then 100 miles east, then 100 miles south. You might think this would make a square, but it wouldn't, because you would not at the end have come back to your starting point. If you have time, you may convince yourself of this by experiment. If not, you can easily see that it must be so. When you are near the pole, 100 miles takes you through more longitude than when you are nearer the equator, so that in doing your 100 miles east, if you are in the northern hemisphere, you get to a point further east than that from which you started. As you walk due south after this, you remain further east than your starting point and end up at a different place from that in which you began. Suppose, to take another illustration, that you start on the equator 4,000 miles east of the Greenwich meridian. You travel till you reach the meridian. Then you travel northwards along it for 4,000 miles through Greenwich and up to the neighborhood of the Shetland Islands. Then you travel eastward for 4,000 miles, and then 4,000 miles south. This will take you to the equator at a point 4,000 miles further east than the point from which you started. In a sense, what we have just been saying is not quite fair, because except on the equator, traveling due east is not the shortest route from a place to another place due east of it. A ship traveling, say, from New York to Lisbon, which is nearly due east, will start by going a certain distance northward. It will sail on a great circle, that is to say, a circle whose center is the center of the earth. This is the nearest approach to a straight line that can be drawn on the surface of the earth. Meridians of longitude are great circles, and so is the equator, but the other parallels of latitude are not. We ought therefore to have supposed that when you reach the Shetland Islands, you travel 4,000 miles not due east, but along a great circle which lands you at a point due east of the Shetland Islands. This, however, only reinforces our conclusion. You will end at a point even further east of your starting point than before. What are the differences between the geometry on a sphere and the geometry on a plane? If you make a triangle on the earth whose sides are great circles, you will not find that the angles of the triangle add up to 2 right angles. They will add up to rather more. The amount by which they exceed 2 right angles is proportional to the size of the triangle. On a small triangle, such as you could make with strings on your lawn, or even on a triangle formed by 3 ships which can just see each other, the angles will add up to so little more than 2 right angles that you will not be able to detect the difference. But if you take the triangle made by the equator, the Greenwich meridian, and the 90th meridian, the angles add up to 3 right angles, and you can get triangles in which the angles add up to anything up to 6 right angles. All this you could discover by measurements on the surface of the earth, without having to take account of anything in the rest of space. The theorem of Pythagoras also will fail for distances on a sphere. From the point of view of a traveler bound to the earth, the distance between 2 places is their great circle distance. That is to say, the shortest journey that a man can make without leaving the surface of the earth. Now suppose you take 3 bits of great circles which make a triangle, and suppose one of them is at right angles to another. To be definite, let one be the equator, and one a bit of the meridian of Greenwich, going northward from the equator. Suppose you go 3,000 miles along the equator, and then 4,000 miles due north. How far will you be from your starting point, estimating the distance along a great circle? If you were on a plane, your distance would be 5,000 miles, as we saw before. In fact, however, your great circle distance will be considerably less than this. In a right-angled triangle on a sphere, the square on the side opposite the right angle is less than the sum of the squares on the other 2 sides. These differences between the geometry on a sphere and the geometry on a plane are intrinsic differences. That is to say, they enable you to find out whether the surface on which you live is like a plane or like a sphere, without requiring that you should take account of anything outside the surface. Such considerations led to the next step of importance in our subject, which was taken by Gauss, who flourished 100 years ago. He studied the theory of surfaces and showed how to develop it by means of measurements on the surfaces themselves, without going outside them. In order to fix the position of a point in space, we need 3 measurements. But in order to fix the position of a point on a surface, we need only 2. For example, a point on the Earth's surface is fixed when we know its latitude and longitude. Now, Gauss found that whatever system of measurement you adopt, and whatever the nature of the surface, there is always a way of calculating the distance between 2 not very distant points of the surface when you know the quantities which fix their positions. The formula for the distance is a generalization of the formula of Pythagoras. It tells you the square of the distance in terms of the squares of the differences between the measure quantities which fix the points, and also the product of these 2 quantities. When you know this formula, you can discover all the intrinsic properties of the surface, that is to say, all those which do not depend upon its relations to points outside the surface. You can discover, for example, whether the angles of a triangle add up to 2 right angles, or more or less, or more in some cases and less in others. But when we speak of a triangle, we must explain what we mean, because on most surfaces there are no straight lines. On a sphere, we shall replace straight lines by great circles, which are the nearest possible approach to straight lines. In general, we shall take, instead of straight lines, the lines that give the shortest route on the surface from place to place. Such lines are called geodesics. On the Earth, the geodesics are great circles. In general, they are the shortest way of traveling from point to point if you are unable to leave the surface. They take the place of straight lines in the intrinsic geometry of a surface. When we inquire whether the angles of a triangle add up to 2 right angles or not, we mean to speak of a triangle whose sides are geodesics. And when we speak of the distance between 2 points, we mean the distance along a geodesic. The next step in our generalizing process is rather difficult. It is the transition to non-Euclidean geometry. We live in a world in which space has 3 dimensions, and our empirical knowledge of space is based upon measurements of small distances and of angles. When I speak of small distances, I mean distances that are small compared to those in astronomy. All distances on the Earth are small in this sense. It was formerly thought that we could be sure a priori that space is Euclidean. For instance, that the angles of a triangle add up to 2 right angles. But it came to be recognized that we could not prove this by reasoning. If it was to be known, it must be known as the result of measurements. Before Einstein, it was thought that measurements confirm Euclidean geometry within the limits of exactitude attainable. Now, this is no longer thought. It is still true that we can, by what may be called a natural artifice, cause Euclidean geometry to seem true throughout a small region such as the Earth. But in explaining gravitation, Einstein is led to the view that over large regions where there is matter, we cannot regard space as Euclidean. The reasons for this will concern us later. What concerns us now is the way in which non-Euclidean geometry results from a generalization of the work of Gauss. There is no reason why we should not have the same circumstances in three-dimensional space as we have, for example, on the surface of a sphere. It might happen that the angles of a triangle would always add up to more than two right angles, and that the excess would be proportional to the size of the triangle. It might happen that the distance between 2 points would be given by a formula analogous to what we have on the surface of a sphere, but involving 3 quantities instead of 2. Whether this does happen or not can only be discovered by actual measurements. There are an infinite number of such possibilities. This line of argument was developed by Riemann in his dissertation on the hypotheses which underlie geometry, 1854, which applied Gauss's work on surfaces to different kinds of three-dimensional spaces. He showed that all the essential characteristics of a kind of space could be deduced from the formula for small distances. He assumed that, from the small distances in 3 given directions, which would together carry you from one point to another not far from it, the distances between the 2 points could be calculated. For instance, if you know that you can get from one point to another by first moving a certain distance east, then a certain distance north, and finally a certain distance straight up in the air, you are to be able to calculate the distance from the one point to the other. And the rule for the calculation is to be an extension of the theorem of Pythagoras, in the sense that you arrive at the square of the required distance by adding together multiples of the squares of the component distances, together possibly with multiples of their products. From certain characteristics in the formula, you can tell what sort of space you have to deal with. These characteristics do not depend upon the particular method you have adopted for determining the positions of points. In order to arrive at what we want for the theory of relativity, we now have one more generalization to make. We have to substitute the interval between events for the distance between points. This takes us to space-time. We have already seen that in the special theory of relativity, the square of the interval is found by subtracting the square of the distance between the events from the square of the distance that light would travel in the time between them. In the general theory, we do not assume this special form of interval, except at a great distance from matter. Elsewhere, we assume to begin with a general form, like that which Riemann used for distances. Moreover, like Riemann, Einstein only assumes his formula for neighboring events, that is to say, events which have only a small interval between them. What goes beyond these initial assumptions depends upon observation of the actual motion of bodies in ways which we shall explain in later chapters. We may now sum up and restate the process we have been describing. In 3 dimensions, the position of a point relatively to a fixed point, the origin, can be determined by assigning 3 quantities, coordinates. For example, the position of a balloon relatively to your house is fixed if you know that you will reach it by going first a given distance due east, then another given distance due north, and then a third given distance straight up. When, as in this case, the three coordinates are three distances all at right angles to each other, which, taken successively, transport you from the origin to the point in question. The square of the direct distance to the point in question is got by adding up the squares of the three coordinates. In all cases, whether in Euclidean or in non-Euclidean spaces, it is got by adding multiples of the squares and products of the coordinates according to an assignable rule. The coordinates may be any quantities which fix the position of a point, provided that neighboring points must have neighboring quantities for their coordinates. In the general theory of relativity, we add a fourth coordinate to give the time, and our formula gives interval instead of spatial distance. Moreover, we assume the accuracy of our formula for small distances only. We assume further that at great distances from matter, the formula approximates more and more closely to the formula for interval which is used in the special theory. We are now at last in a position to tackle Einstein's theory of gravitation. Chapter 8: Einstein's Law of Gravitation. Before tackling Einstein's new law, it is as well to convince ourselves on logical grounds that Newton's law of gravitation cannot be quite right. Newton said that between any two particles of matter, there is a force which is proportional to the product of their masses and inversely proportional to the square of their distance. That is to say, ignoring for the present the question of mass, if there is a certain attraction when the particles are a mile apart, there will be a quarter as much attraction when they are 2 miles apart, a ninth as much when they are 3 miles apart, and so on. The attraction diminishes much faster than the distance increases. Now, of course, Newton, when he spoke of the distance, meant the distance at a given time. He thought there could be no ambiguity about time, but we have seen that this was a mistake. What one observer judges to be the same moment on the earth and the sun, another will judge to be 2 different moments. Distance at a given moment is therefore a subjective conception, which can hardly enter into a cosmic law. Of course, we could make our law unambiguous by saying that we are going to estimate times as they are estimated by Greenwich Observatory, but we can hardly believe that the accidental circumstances of the earth deserve to be taken so seriously. And the estimate of distance also will vary for different observers. We cannot therefore allow that Newton's form of the law of gravitation can be quite correct, since it will give different results according to which of many equally legitimate conventions we adopt. This is as absurd as it would be if the question whether one man had murdered another were to depend upon whether they were described by their Christian names or their surnames. It is obvious that physical laws must be the same, whether distances are measured in miles or in kilometers, and we are concerned with what is essentially only an extension of the same principle. Our measurements are conventional to an even greater extent than is admitted by the special theory of relativity. Moreover, every measurement is a physical process carried out with physical material. The result is certainly an experimental datum, but may not be susceptible of the simple interpretation which we ordinarily assign to it. We are therefore not going to assume to begin with that we know how to measure anything. We assume that there is a certain physical quantity called interval, which is a relation between two events that are not widely separated. But we do not assume in advance that we know how to measure it, beyond taking it for granted that it is given by some generalization of the theorem of Pythagoras, such as we spoke of in the preceding chapter. We do assume, however, that events have an order, and that this order is four-dimensional. We assume, that is to say, that we know what we mean by saying that a certain event is nearer to another than to a third, so that before making accurate measurements, we can speak of the neighborhood of an event, and we assume that, in order to assign the position of an event in space-time, four quantities, coordinates, are necessary. E.g., in our former case of an explosion on an airship, latitude, longitude, altitude, and time. But we assume nothing about the way in which these coordinates are assigned, except that neighboring coordinates are assigned to neighboring events. The way in which these numbers, called coordinates, are to be assigned is neither wholly arbitrary nor a result of careful measurement. It lies in an intermediate region. While you are making any continuous journey, your coordinates must never alter by sudden jumps. In America, one finds that the houses between, say, 14th Street and 15th Street are likely to have numbers between 1400 and 1500, while those between 15th Street and 16th Street have numbers between 1500 and 1600, even if the 1400s were not used up. This would not do for our purposes, because there is a sudden jump when we pass from one block to the next. Or again, we might assign the time coordinate in the following way. Take the time that elapses between two successive births of people called Smith. An event occurring between the births of the 3000th and the 3001st Smith, known to history, shall have a coordinate lying between 3000 and 3001. The fractional part of its coordinate shall be the fraction of a year that has elapsed since the birth of the 3000th Smith. Obviously, there could never be as much as a year between two successive additions to the Smith family. This way of assigning the time coordinate is perfectly definite, but it is not admissible for our purposes, because there will be sudden jumps between events just before the birth of a Smith and events just after, so that in a continuous journey, your time coordinate will not change continuously. It is assumed that, independently of measurement, we know what a continuous journey is, and when your position in space-time changes continuously, each of your four coordinates must change continuously. 1, 2, or 3 of them may not change at all, but whatever change does occur must be smooth, without sudden jumps. This explains what is not allowable in assigning coordinates. To explain all the changes that are legitimate in your coordinates, suppose you take a large piece of soft India rubber. While it is in an unstretched condition, measure little squares on it, each 1/10 of an inch each way. Put in little tiny pins at the corners of the squares. We can take as 2 of the coordinates of one of these pins the number of pins passed in going to the right from a given pin, until we come just below the pin in question, and then the number of pins we pass on the way up to this pin. In the figure, let O be the pin we start from, and P the pin to which we are going to assign coordinates. P is in the 5th column and the 3rd row, so its coordinates in the plane of the India rubber are to be 5 and 3. Now take the India rubber and stretch it and twist it as much as you like. Let the pins now be in the shape they have in figure 2. The divisions now no longer represent distances according to our usual notions, but they will still do just as well as coordinates. We may still take P as having the coordinates 5 and 3 in the plane of the India rubber, and we may still regard the India rubber as being in a plane, even if we have twisted it out of what we should ordinarily call a plane. Such continuous distortions do not matter. To take another illustration, instead of using a steel measuring rod to fix our coordinates, let us use a live eel, which is wriggling all the time. The distance from the tail to the head of the eel is to count as 1, from the point of view of coordinates, whatever shape the creature may be assuming at the moment. The eel is continuous, and its wriggles are continuous, so it may be taken as our unit of distance in assigning coordinates. Beyond the requirement of continuity, the method of assigning coordinates is purely conventional, and therefore a live eel is just as good as a steel rod. We are apt to think that for really careful measurements, it is better to use a steel rod than a live eel. This is a mistake, not because the eel tells us what the steel rod was thought to tell, but because the steel rod really tells no more than the eel obviously does. The point is not that eels are really rigid, but that steel rods really wriggle. To an observer in just one possible state of motion, the eel would appear rigid, while the steel rod would seem to wriggle just as the eel does to us. For everybody moving differently, both from this observer and ourselves, both the eel and the rod would seem to wriggle. And there is no saying that one observer is right and another wrong. In such matters, what is seen does not belong solely to the physical process observed, but also to the standpoint of the observer. Measurements of distances and times do not directly reveal properties of the things measured, but relations to the things to the measurer. What observation can tell us about the physical world is therefore more abstract than we have hitherto believed. And now that live eels have entered the picture, that seems as good a place as any to end this evening's reading from the ABC of Relativity by Bertrand Russell. This book always leaves me thinking, which I rather appreciate, and I hope you enjoy it as well. If you'd like to read this fascinating work for yourself, as always, you'll find a link to a free ebook from Project Gutenberg in the show description. If you'd like to connect, suggest a boring book you'd like to hear read, or request more from one we've already started, you can drop me an email via our website, www.boringbookspod.com. It's always a pleasure to hear from you. Thank you so much for joining me for this evening's reading. Until our next boring book, good night.